Hey, hi everyone. My name is Jeff Cardill from McGill University in the Department of Natural Resource Sciences and the Beeler School of Environment. And as part of this chapter discussion, I'm going to introduce you to the topics that we'll cover in the chapter itself, bulk and bulk T. So what I want you to first think about is this idea of loaded dice. So we've all played with dice. Six-sided die with numbers on each side. And there's evidence of loaded dice going all the way back as far as we have records of there being square die that are used, cubic die that are used. Here, there was some way that the top was cut off. These are dice that were found in the ruins of Pompeii. Dice was cut off, and I think there was maybe some lead put on one side. The result is it became more heavy on one side than another. And so these die were more likely to roll a particular number than would be likely in a normal set of dice. So what I want you to do is just think for a moment about what we would see. And when we see that, what we would tell someone would be our estimated probability of whether these are loaded dice or not. So if I first rolled a 2, you would say, I have no real reason to believe that these are loaded dice. If I rolled another 2, you might say, well, chances of that are 1 out of 36, it can happen. Then if I rolled a third 2, that might really change your sense of what the probability of these being loaded dice are. Maybe 30%, maybe 80% for some people. Then if I rolled a fourth die, I would bet that almost everybody would think that is absolutely not correct. A person who's a statistician might say, I'm going to multiply 1/6 times 1/6 times 1/6 times 1/6, and whatever that is, that's my estimate of the probability that these are loaded dice. That probably is somewhere less than 100%. I would be willing to bet a lot of money, I think, on them being loaded dice if we saw 4 2s in a row. Then if I saw a fifth 2 in a row, I think I would still be about 100% confident. Now, our estimated probability might look something like this, but what if we got a 6 in the middle? We had a 2, a 6, and then another 2 and another 2. We might say, well, when I get the 2 and the 2 and the 6, I don't think it's likely that they're loaded dice. But when I see the third 2 out of 4, I might say, actually, it's almost maybe 50-50 as to whether these dice are strange in some way. And then if I saw the fourth 2, I would say, I myself would bet that those are loaded dice to see 4 2s out of 5. Even if I didn't then go do the statistics, most people would not be capable of doing the statistical calculation of what that probability is. And yet, I think anyone we talk to would be able to have a sense of how likely that seemed or how unlikely that seemed. So that feeling of our sense of confidence is what I think of as the idea of Bayesian statistics, the goal of Bayesian statistics. So in the world of remote sensing, I think of it as what can we learn by accumulating a bunch of evidence from a lot of different sources. And so with bulk, which stands for Bayesian updating of land cover, we use Bayesian stats in order to make estimates about the probability of different states of land use and land cover. And so this slide shows over in the lower left, you may remember from being a little kid, maybe where you were, there are little series of flip books with little pictures on them. You flip through the book and you can see a person do a somersault or wave, something like that. And even though there are scratches or maybe one of the pages has a kid colored on it, or maybe one of the pages is torn out, we can still have the feeling of watching the thing change through time. The same thing, I think, is also possible with seeing lots of classifications through time. And so we have a mathematical foundation for applying Bayes' algorithm that is contained in our papers. And the effect is to go from having images that are on the top, where you see raw imagery. This is of a fire in Quebec in 2016, I think. We then make these provisional classifications that we know have errors in them, but we don't necessarily know where those errors are. And yet, if we move as a human with our eye across the screen from left to right over here, you can probably just almost instinctively ignore the fact that there's a stripe here. You may not even notice it when we look at it, or notice that this area is blank. Maybe we notice it for a second and then say, yeah, but I can see the image down here too. That's in effect what bulk does with the arithmetic that it does to calculate the Bayesian probability. And so this is the bulk derived map of the classification in that area over time. And so in the case that we highlighted for this paper, which you can look up if you'd like to, we have these, what we call event classifications. That's a term from Bayesian stats, which is the receiving evidence. It's called an event. And then our posterior probabilities, in other words, our results up to that point of what we think those probabilities are. This is a very, very rough accuracy estimate. Nevertheless, we can see, I think, pretty easily that the accuracy of these maps, especially this map, let's say, is much lower. That's this one here, I think, is much lower than the one of the synthetic image that we have. So we later discovered that this same code allowed us to sharpen existing classifications. We took a very rough classification from the globe cover 2009 classification at 300 meters on a side. You can see it just coming around now. And as we fed it unsupervised events, unsupervised classifications over on the right, the bulk classification was able to kind of pull the information from those classifications and use it to refine, both to correct errors in the globe cover classification and to sharpen the resolution to a finer resolution than we had before. So it was pretty amazing to watch it converge. You can see maybe just a little suggestion of how it converged over 6 or 8 images. And we were pretty conservative and said, yeah, over the course of 10 images, it's conserved. And so here you can see much more close, in a close-up of that area. You can see that the globe cover classification is quite good as a 300-meter classification. And yet, if we have this additional evidence available, we can use bulk, this Bayesian concept, to sharpen that classification and to do some correction of that classification also. We also then used it. This is again my same master student as on the previous stuff, to sharpen the classification and go back in time. So this is a bulk U, the endpoints from 1986 to the year 2000 of an area in Brazil. And we created a time series that we don't show on this slide, but here each, maybe we had 30 or so images from 1986 to 2000. And so we kind of grew this, well, we actually rolled it in reverse, took this classification and fed it the images in reverse to produce this old classification or classification from the past. And we then took the same images and rolled them forward in time to reproduce this bulk U 2000. So it has this neat characteristic of being able to go forward and backward in time, and also to take in data from a lot of different sources. And that's what we have shown on this slide here. In a paper from, I guess, a couple years ago now, we have classifications or a bunch of imagery shown here on the left. On the left are images from a lot of different sources. So Landsat 1, 2, 3, and 4, you might know that those are at 60-meter resolution. They're much coarser than Landsat 8, Landsat 9, and Sentinel-2 that we have now. And we have a bunch of other sensors that are available to us as well. We created a simple, rough classification, not trying to be perfect in any of these provisional classifications, produced one for each of them, and then sent them to bulk. So the action of bulk is going from this center panel to the right panel, where we create this land cover series. And so that's the idea of how that part works. We then also have the ability to use Dynamic World, which produces multiple classifications of every, or one classification of every Sentinel-2 image as soon as they come in. If you think about it, this must be the largest set of land cover classifications that has ever been assembled. We have thousands or tens of thousands, I suppose, of land cover classifications now being produced every day. And so I think we will really benefit from having strategies for sifting through the evidence from those classifications. And that's what we'll do in the lab today. You'll see sort of a version of this set here, where we have, here's a time series of the events that we get from Dynamic World. You can see, in a similar way to what you saw with the fire a few minutes ago, you can see kind of a rhythm to the classifications, but you probably would not want to exactly strictly believe that a lot of pixels were this light green color and then changed to this color for one day and then switch back to the yellow color and then back to that greenish color. And so this is what bulk can do, is to give us the composite sense of what those classifications tell us, also to give us some idea of the confidence. And then we're able to sort of draw the two together with a cool technique from the same person who wrote chapter 1.0. We're also, a thing that we'll do today is we're also able to reclassify the Sentinel data into the Sentinel classifications from being 8 or 9 or 10 categories into whatever categories we want. We'll show you how to do that, and then do the same thing. And what that shows is, from the perspective of having just 3 classifications, there's not really as much uncertainty in the classification as you move from left to right. And so the confidence is more even, I think, in space. Although at the edges of phenomena, like at the edges of a river and forest, they're still kind of flipping back and forth. And so this might be useful for people who want to try to understand what happens in a lot of different places. And so the idea, just to finish, and this is I think the very last of these slides, is that we are able to produce land use and land cover classifications at 10 meters from Sentinel-2 that you can create anywhere on Earth using the bulk interface. And so now I'll turn back to the book and we can go through the chapter.